Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. We are returning to space tonight. This journey is going to be our biggest ever. We are not just going to visit a particular planet or a part of the solar system. No, by the power of imagination, we're going to accelerate to several thousand times the speed of light. We will escape the solar system in a matter of seconds and travel to other galaxies. Along the way, I will tell you about our galaxy, the Milky Way. We will discuss other galaxies too, like our destination, Andromeda. I will explain the mind-blowing distances within and between galaxies, their populations of billions and billions of star systems, how the existence of galaxies was discovered and how they are observed. We will discuss mysteries like the possibility of life on these hundreds of billions of planets they contain, the possible existence of invisible dark matter in the universe, and how fast it is possible to travel in space. As usual, you don't need to worry about the complexity of all this. Everything is going to be easy to understand even without knowledge of physics or astronomy. Everything will fall into place if you just let the sound of my voice guide you and to keep an open mind. But first, I would like to take a few seconds of your time to let you know that we have a Patreon page for those of you who wish to and can support this project. Get more of it and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3 per month, but it doesn't mean you get less. We let people contribute what they wish to or they can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. If you join, you will gain access to various new features. For example, you will have the option to listen to all episodes with or without background sounds. You will have the ability to download all these audios and participate in selecting future topics. And also direct communication with us to give us your feedback. We also offer advanced releases and updates on upcoming episodes. There are several stories only available to our patrons, and we add new ones frequently. We have added a link to our Patreon page in the description of the episode. But before we begin, let's take a moment to prepare for our journey ahead. If you'd like, gently close your eyes and let your daily concerns drift away. Find a position that feels natural and cozy. Perhaps make small adjustments until you're perfectly comfortable. Now, draw in a deep breath, a nourishing one, and as you release it softly, notice how your body responds. Feel the warmth flowing from your shoulders down through your neck, melting away any tension. Let your facial muscles become soft, your jaw loose, your fingers naturally open, and your legs completely at ease. And as you settle into this peaceful state, my voice will be your gentle companion as we begin our exploration together. We will soon leave Earth and go further than any human has gone before. The Andromeda Galaxy, our destination, is extraordinarily far, and yet you probably have already seen it. On a moonless night, and from areas with limited light pollution, it is so large that it can be visible to the naked eye from our planet. It appears in the same area of the sky of the constellation of Andromeda, hence the name given to the galaxy. Even though it is way, way beyond the stars that form that constellation of Andromeda. Before we reach this galaxy, we're going to accelerate beyond imagination, even beyond what the law of physics, as we know them, probably allow. We will come back later to that. But first, let's take a look at where our planet is in our galaxy. We are used to thinking about the position of Earth relative to other bodies in the solar system, the Sun at the center of it, and then the other planets and bodies that orbit the Sun. But the Sun is just one star among hundreds of billions that also orbit around another center, the center of the Milky Way. The understanding that we are part of a much larger disk of stars is recent, only a century ago. The Milky Way is shaped like a gigantic flat disk. When bodies orbit around the center, they tend to align on the same plane. This is an effect of gravitational forces that keep them together. They tend to align on a plane. But star systems or galaxies are not perfectly flat. The Milky Way's disk is 1,000 light-years thick and is estimated to be 100,000 light-years wide in diameter. So it is about 100 times wider than it is thick, like the proportions of a CD-ROM. Sometimes in pictures, galaxies are represented with an oval shape, but this is because they are represented seen from the side with an inclination. If an observer looked at the Milky Way at the vertical of its center, the galaxy would look circular. All galaxies are not alike. On our way to Andromeda, we will soon reach a dwarf galaxy that may be in the process of being torn apart by the Milky Way. Some galaxies have only tens of millions of stars. Others have hundreds of billions, and their shapes vary too. Among large galaxies, there are three shapes that have been observed. The most frequent ones, like our own, are spiral galaxies. Their stars are organized on a disk, but they concentrate on arms originating from the center. And most spiral galaxies have a central concentration of stars known as the bulge. This is why the center appears more luminous. In the periphery, these spiral galaxies have a much fainter halo of stars. The arms appear more luminous because they contain a higher concentration of stars, often younger stars that shine brighter. It is believed that these stars are born from nebulae, which are giant clouds of gas and dust. Sometimes part of the nebulae collapse onto themselves after a shock wave hits them, and the gravitational forces lead to the accretion of this matter into a new star and eventually planets around it. The Milky Way contains various nebulae. They are the matrix of star systems. And when a star dies after billions of years because its fuel is exhausted, it may disintegrate and give back the matter it was made of to a nebula. The majority of spiral galaxies also have a bar-like structure that extends from the bulge. The Milky Way has one. Its spiral arms begin at the end of the bar. Not all galaxies are spiral shaped, though. Another type is elliptical galaxies. These ones have an ellipsoidal shape, which is like a sphere that has been slightly flattened. Seen from afar, they look like a smooth and nearly featureless halo of light, with more luminosity in the center where the more stars are concentrated. It was believed when these elliptical galaxies were discovered that they were younger and they could later evolve into spiral galaxies. But we now know that this is not the case. In fact, the stars they contain are, on average, much older than the stars found in spiral galaxies. And finally, there is a last shape, irregular galaxies, which are the ones with no distinct regular shape. These ones are chaotic in appearance. They have no bulge in the center, so they are like clouds of stars. Some irregular galaxies probably once were spiral or elliptical, and they were deformed by an external shock or gravitational force. Generally, these irregular galaxies are much smaller, about 1/10 of spiral galaxies, and this small size makes them more prone to crash and eventually be absorbed by larger galaxies. This typology of galaxies was started by an American astronomer called Edwin Hubble, the same Hubble whose name was given to the Hubble telescope. He is one of the most important astronomers of all time because he extended our understanding of the cosmos way beyond the limits of his time. He was active in the first half of the 20th century. His main findings include the discovery that clouds of dust or gas that were visible from the Earth and were thought to be nebulae were in fact galaxies beyond the Milky Way, and that the Milky Way was just one galaxy among many others. So he would start to map visible objects in the sky of the Earth and differentiate what was part of our galaxy and what was at the extragalactic distance. Together with the works of other astronomers, he also contributed to discovering that galaxies that were more distant from Earth tended to recede quicker. This is important because this is a clue that the universe is expanding, and it became one of the elements that backed the Big Bang Theory and made it go mainstream. Since its elaboration, the Big Bang Theory has been backed by various proofs of that kind that it accurately describes the history of the universe. So, where are we inside our spiral-shaped galaxy? The answer is midway between the center and the side. The radius of the Milky Way is 50,000 light years, and we are approximately 25,000 light years away from the center and 25,000 light years away from the edge. To exit the galaxy, we could either travel along the disk, and at light speed, it would take 25,000 years. Or for a shorter exit, we could travel following the perpendicular to the galaxy's plane. And that would be faster, but would still require several centuries at light speed. This gives us an idea of the size of our galaxy. We are disproportionately small and slow to even imagine reaching the edges of the Milky Way, let alone travel to another galaxy. Andromeda is 2.5 million years away from Earth. This means that what we see when we look at the sky and see Andromeda are rays of light that the galaxy emitted 2.5 million years ago. If it were to disappear entirely, we would be informed of it 2.5 million of our years after the fact. The fastest spaceships ever built travel at a small portion of light speed, way less than 1% of it. But even if we could reach light speed or close, traveling to other systems in our galaxy would remain a very long journey. The diameter of the Milky Way, you remember, is estimated at least 100,000 light years. And there are generally several light years between star systems. So reaching another galaxy would remain very implausible. But if we suppose technical limitations can be overcome, is it possible to move faster than light? Our understanding of physics implies that very probably not, at least not for human beings made of matter as we know it. According to the theory of relativity, when a body with a mass, a measurable quantity of matter, accelerates close to light speed, its mass precipitously increases and becomes infinite, and so does the energy required to move it. So this is impossible. The light, photons that travel at light speed have no mass, and this is how they can travel so fast without seeing their mass tending towards the infinite. The increase in mass when matter accelerates and comes close to light speed has been verified in particle accelerators. In a particle accelerator, particles like electrons are propelled to observe their properties when they accelerate or when they collide. In the 1960s, scientists observed that at some point when the electrons accelerated, they needed to provide them with more and more energy to make them keep accelerating. And even though electrons came close to light speed, they could never quite reach it because they got heavier and heavier. And it is obviously impossible to provide them with the infinite quantity of energy that could move their infinite mass. Our bodies and everything we build are made of the same matter that can be tested in particle accelerators. And they are subject to the same laws, the same limitations. So it looks impossible, or at least implausible, that a human being will ever travel at light speed. For now, this is not really a problem even for the fastest man-made vehicles, because they are way slower than light speed. For example, one of the fastest flying objects ever built is a space probe called New Horizons. This probe reached the limits of the star system a few years ago. It reached a speed of 16 kilometers per second, about 10 miles per second. 16 kilometers per second is already a speed that defies our imagination. For example, it puts Los Angeles at less than 5 minutes from New York City, and a complete journey around the Earth would take only 45 minutes. But this is still very slow in comparison with light speed. Light doesn't need 45 minutes to travel around the Earth. It needs just a bit more than 1/10 of a second. It travels almost 20,000 times faster than the New Horizons probe. But even assuming that we could build vehicles that are thousands of times faster, and we could come close to light speed, interstellar travel would remain very difficult, very long, and intergalactic travel still out of reach. Okay, so now if traveling in a straight line is impossible, maybe another option would be to use shortcuts. We figure out that the universe is a three-dimensional space because this is a perception that our senses and our minds have. We know since Einstein's theory of relativity that this perception is just one aspect, one way of seeing the universe, and probably a very incomplete, partial one. A few scientists and many sci-fi authors have considered the possibility that shortcuts in the structure of our universe, shortcuts in space-time, could be found or even created to almost instantly travel to another point in the universe in what would be some sort of teleportation. Theoretically, the theory of relativity allows the existence of structures called wormholes that would link disparate points in space-time, like tunnels, with two ends that would connect different points in space, different universes, or different points in time. But this is completely hypothetical, and no wormhole has ever been identified. However, science fiction quickly embraced the concept decades ago because it was a way to explain or justify very long distance travels in a short time and give stories a varnish of scientific credibility, which is why the concept of wormhole has become quite famous. Even though the existence of wormholes is far from certain, maybe one day a wormhole could be identified. After all, black holes also were a very hypothetical, theoretical kind of object for a long time before they were finally observed. Wormholes would be pre-existing structures, but maybe this type of tunnel could also be created and controlled by actively distorting space-time, which would allow a spacecraft to create its own shortcut to another point in the universe. This is also highly speculative, and there is no chance to see that kind of craft anytime soon, because we have no idea how to do that, or how to power such a spacecraft. At this point, we have no grip and no clue about how to actively modify space-time, if that's possible. But once again, science fiction is ahead, and that sort of modification of space-time to allow a ship to travel to other points in space or to another dimension is already familiar in fiction. Sometimes it includes a very cliché scene where someone folds a sheet of paper to show that any 2 points apparently distinct on a plane can be reunited, and the distance between them reduced to 0. This method of teleportation amounts to creating a man-made hole. But let's return to our journey for now. We are still not at cruise speed, but we already are traveling in imagination at hundreds of times light speed. We have left the solar system behind, and we are now in an interstellar void, on our way to the closest star system to Earth, Alpha Centauri. Alpha Centauri already gives us a glimpse of the diversity of stars and systems in our galaxy. At only 4 light years from Earth, it is not a single star system with planets orbiting around their star, like the solar system. It has 3 stars. 2 of them are rather similar to the Sun, and they orbit together around a common center, forming a binary star. From the Earth and to the naked eye, they look like one single star that appears in the constellation of Centaurus, hence the name of the system. But they are not alone. There is a third, less visible star that is almost invisible from Earth, Alpha Centauri c, or Proxima Centauri. This star is called a red dwarf. Red dwarfs are smaller and cooler than sun-like stars, which makes them harder to spot because they don't emit as much light. Red dwarfs are very abundant. It is estimated that they represent more than half the stars in the Milky Way, and they can also potentially exist for way longer than other types of stars, because when they burn their fuel, atoms of hydrogen merging together to create helium in the core of the star, the resulting helium is evacuated from the core by a convection movement. This means that the fusion reaction can last a long, long time. Red dwarfs are estimated to be able to burn for thousands of billions of years, as opposed to mere billions of years for more shiny stars. This lifespan represents much, much more than the average of the universe, estimated at about 14 billion years. So all red dwarfs are still very young, and none of them can exist at an advanced stage of evolution. Proxima Centauri orbits around the two other bigger stars. The system remains little known, but planets have been discovered in it, including one called Proxima Centauri b, that orbits around the red dwarf. This planet is the closest exoplanet to Earth that has been discovered until now. Exoplanets just means planets outside the solar system. I have a story on exoplanets in my library if you want to check it out later. This one, Proxima Centauri b, is in the so-called habitable region around its star. Habitable region means that, in theory, given the distance to the star, the planet could have conditions of temperature or radiation that could possibly be compatible with the existence of organic life on it. Now that we have reached Proxima Centauri, we're going to accelerate even further and travel thousands of light years in mere minutes to reach the edge of the Milky Way. As we start to see it from the outside, we may notice that the entire galaxy is spinning around its center. We will see later, when we arrive at Andromeda, what lies in the center of the galaxy. It may all look very slow because of the distance, but all star systems orbit around the center at high velocities. For example, the Sun and the Earth travel at 230 kilometers per second relative to the center of the Milky Way. This is about 143 miles per second. This is less than 1/1000th of light speed, but much faster than the speed of Earth relative to the Sun. The Sun's orbit around the center of the Milky Way is so large that it takes more than 200 million years to complete a revolution. This period of 225 to 250 million years is called the galactic year, or cosmic year, and it represents entire eras for our planet. Even dinosaurs, if we accept birds did not exist for long enough to complete a galactic year. Humanity has been around for only a small fraction of a cosmic year. I told you earlier that Andromeda was the closest galaxy to the Milky Way, but this is actually disputed. It is the closest large spiral galaxy, but there are many other smaller galaxies in the proximity of the Milky Way. One of them is the Canis Major Galaxy, or Canis Major Overdensity, because its status as a galaxy is unclear. This would be an irregular galaxy, located in the same part of the sky as the constellation Canis Major, seen from the Earth. This galaxy would contain about 1 billion stars, which is not much compared with the Milky Way that has at least 400 billion stars. This galaxy, or overdensity, would be in the process of being torn apart and absorbed by the Milky Way. Maybe Canis Major came too close to the Milky Way. In any case, it appears to be losing stars to the gravitational pull of our galaxy, and it forms a trail of stars around the Milky Way. But it isn't clear whether it is or was a distinct galaxy, or just a part of the Milky Way's halo of stars. In any case, an existing theory is that galaxies may grow in size over time by absorbing smaller neighbors. Now let's leave the Milky Way behind and accelerate again to reach Andromeda in a matter of minutes rather than millions of years. We are now in the intergalactic void, which is not very different in nature from the void between bodies inside a galaxy, except it is even more gigantic. It is as close as you can get to absolute vacuum. But there is not nothing at all. On average, estimates point to probably 1 atom of hydrogen per cubic meter. But in some regions of intergalactic space, there are more things. There are clouds of gas ripped away as galaxies interact or sometimes collide. It is difficult to study the intergalactic medium because visually it sends us close to nothing. Only light-emitting or light-reflecting objects like stars can be seen from Earth. Optical light is not very useful, but it is possible to study how light from galaxies that are further away travels through this medium and make hypotheses based on the information. For example, we know there are clouds of gas because some of the light gets absorbed as it travels through intergalactic space. But there is more than gas. The Hubble telescope has observed stars that are not part of a galaxy and exist between galaxies. They may have once belonged to a galaxy, but they were separated from it. These stars are called stellar outcasts or intergalactic stars. And they are not that rare, even though they represent a very small percentage of existing stars. Several hundreds of these free stars have been detected already in space between galaxies. Instead of orbiting around a galaxy center, these stars have been found orbiting around a cluster of galaxies, because galaxies are not the biggest unit in the universe. They tend to be located in groups where they are closer to one another in clusters, like the gas clouds I told you about before. These stars were probably ripped off the galaxy where they formed and belong to via the interaction or collision between galaxies. We don't know how many could be out there, but all the intergalactic stars detected were giants. There may be considerably more that are harder to identify, taking with them their satellites, their planets that accompany them on their lonely travel in space. If we look ahead now, we can see the spiral of Andromeda growing bigger every minute, with its arms spinning around the center. The observation of Andromeda and other galaxies is what has led to one of the most fascinating mysteries and hypotheses in astrophysics: the supposed existence of dark matter. So, what is this about? It all started in the 1930s. By then, the laws of gravitation that we think determine the movement of all bodies in the universe when they have a mass and how these bodies interact were already well understood. But a number of abnormalities were detected, in particular galaxies that seemed to travel faster than they should have, or not exactly in the right direction. This ghost force that seemed to drive the galaxies in the cosmos remained mysterious, and there were not enough observations made with the limited technical means of the time, so that this apparent abnormality was left unexplained for decades. But one hypothesis was elaborated by an astronomer called Fritz Zwicky to explain the speed of galaxies. To explain this, he attributed them more mass than was thought, a mass that would be invisible. By doing this, he managed to explain their motion, and he called this additional matter dark matter because it was invisible. But then there was no immediate follow-up to his work on this until the 1970s, and in particular until the works of another astronomer, Vera Rubin. She observed the movement of the stars spinning around the center of their galaxies and noted that stars that were far from the galactic center were moving way faster than they should. What the laws of gravitation tell us is that the speed of a body orbiting another object depends on the mass of the central object and the distance between them. This is why in the solar system, for example, planets that are closer to the sun travel faster than planets that are far away. Their speeds range from 44 kilometers per second for Mercury, the closest planet to the sun, to 5 kilometers per second for Neptune. Earth is in between, moving at 30 kilometers per second. Now, if we apply the same logic to a galaxy, the stars that are closer to the galactic center should travel way faster than stars that are far from it, close to the ends of the galaxy's arms, except they don't. Stars that are 10 times further away from the galactic center in a galaxy like Andromeda, for example, travel as fast as stars that are way closer to the center. This is unexplainable by gravitation force, except if there is actually more matter than thought. And in fact, she worked on the hypotheses that a cloud of invisible matter existed around the galaxies, which would explain how they move relative to one another, and also the motion of speed of the stars that belong to them. But the problem is, a lot of this invisible or dark matter is necessary to explain the movement of stars, for example, in the Milky Way. It would have to be close to 90% of the total mass of the galaxy. In other words, 90% of the matter contained in our own galaxy would be invisible and unknown. This is not easy to believe. And since Vera Rubin's hypothesis, one of the questions that keep astrophysicists busy is, what is this mysterious dark matter? There are three possible explanations here. The first explanation would be that dark matter is mainly objects that are known to us, but hard to detect because they emit very little light to us, like black holes, gas clouds, or red dwarfs. We know these bodies exist, and some have been detected. But even assuming there would be many, many, many more, the sum of their masses remains far from sufficient to explain the effect of dark matter. Too much mass is missing. The second explanation would be that there are particles out there that we don't know of and have never observed because they would not interact with light. What could be these mysterious particles? We don't know. Despite attempts to detect or even fabricate them in particle accelerators, nothing has been found until now. The third and last explanation, but it is unsettling, would be that the equations of gravitation are incorrect, and that a new theory of gravitation or something entirely new to replace it has to be elaborated. Various puzzling observations have been made. For example, a galaxy called Dragonfly 44 would have to be made of 99% dark matter to explain its trajectory. Other galaxies would be almost entirely devoid of dark matter, meaning that the distribution of this matter would be extremely uneven, depending on the galaxies. But at this stage, astrophysicists have had to conclude that either close to 80% of matter in the universe is unknown and has not been observed yet, or that the laws of gravitation are not accurate and need to be revisited entirely. Maybe in the future an explanation to this mystery will emerge. But in the meantime, it reminds us of how little we know about the universe still. We are now in the immediate vicinity of Andromeda, which looks a lot like the Milky Way because it has a spiral shape, but it is larger. Its diameter is twice the diameter of our galaxy. However, the mass of Andromeda would be rather similar at about 1,000 billion times, 1 trillion times the mass of our Sun. Like the Milky Way, Andromeda has its own system of satellite galaxies. Canis Major was mentioned earlier for the Milky Way, even though it is disputed as a galaxy. But the Milky Way has more than 15 dwarf galaxies that are proven to be part of the same system, and Andromeda would have a similar number. Given their trajectories, the Milky Way and Andromeda are expected to collide in roughly 4.5 billion years, and their merger would form a giant elliptical galaxy. Andromeda would have formed 10 billion years ago. That would be 3 to 4 billion years after the Big Bang, and the galaxy would be the product of the collision of smaller galaxies. In its first billion years, Andromeda was probably very active, with a high rate of star formation. But over the past 2 billion years, it is thought that the formation of new stars throughout this galaxy has almost stopped, and the youngest stars in the galaxy would all come from the captures and mergers with its satellite galaxies. These captures leave what are called stellar streams, and these streams are the remains of dwarf galaxies that have been torn apart and stretched along their orbit. Now that we can see the Milky Way from afar, we could see these stellar streams that may not be aligned with the galaxy's plane. Like our galaxy, Andromeda has hundreds of billions of star systems and hundreds of billions of planets too. It is really in the 20th century that we have realized that the universe was much, much bigger than thought before, or at least that it contained more objects than thought. Because until the appearance of the Big Bang Theory, the universe was estimated to be infinite and eternal, which was a guess based on the very limited information physicists had available. Another breakthrough in the 20th century was that the understanding of organic life and the physical and chemical processes that led to its appearance. Even though everything is far from explained and science only answers the how of things, not the why they ultimately happen. This is a metaphysical question. However, it looks well possible that the same physical conditions that have led to the appearance of life on Earth, or other conditions maybe, could also exist in other parts of the universe. The laws of chemistry are the same on other bodies in space, and the molecules that can combine to create organic life are relatively abundant in the universe. So even though the probability that it happens on a particular planet or satellite is very low, when you multiply that low probability by hundreds of billions for the number of planets in a galaxy, and then again by billions more for the number of galaxies, you can quickly conclude that the existence of life in other parts of the universe is a near certainty. Maybe it could even exist or have existed close to us in the solar system, on the moons of Jupiter, or even on Mars in the past. We also know that the universe was already 10 billion years old when the first traces of life, the first unicellular organisms, appeared on Earth, and other planets formed billions of years before Earth. But if life can appear in multiple parts of the universe and evolve like it did for us into conscious beings that could travel away from their planet of origin or send information like radio waves, how is it that nothing has been detected yet and that they haven't found us? The apparent contradiction between the absence of signs of extraterrestrial civilizations and the high probability that they exist, may be more ancient than ours, is called the Fermi Paradox, after a physicist called Enrico Fermi, who participated in a famous conversation about this. Arguably, it takes a long time to travel in the entire Milky Way, maybe millions of years at subluminal velocity. But millions of years is not much when the age of most stars and planets in the galaxy is several billion years. we should have found or detected probes, or at least signs of intelligent life that can travel faster, like radio waves. The question was raised by Fermi in this conversation in the 1950s, but even before him, it appeared in a manuscript by Russian scientist Konstantin Tsiolkovsky in the 1930s. Under the same terms, how is it possible that the near certainty of the existence of intelligent life is nowhere to be found? Tsiolkovsky proposed one of the numerous explanations to this apparent paradox, what is called the zoo hypothesis. This hypothesis speculates that extraterrestrial life intentionally refrains from contacting Earth and humans, either because they are not interested — what could we know about their motivations anyway? — or because they want to allow for natural evolution, avoiding contamination. But they could be observing us like visitors observe animals at a zoo. Another possible explanation, called the rare earth hypothesis, is that the set of circumstances that led to the appearance of life and then the evolution of biological complexity is very rare or even unique to Earth. This hypothesis argues that there are so many conditions required for Earth-like life that this phenomenon is indeed almost unique. It takes a planet in a habitable zone of a star system, a guardian against collisions by asteroids, in the case of the solar system, Jupiter, a large moon, a magnetosphere to be shielded from solar radiations, an atmosphere, and oceans. And yet another filter is the transition from unicellular life to more complex organisms, which on Earth took hundreds of millions of years and may be a very unlikely event. If we follow the rare Earth hypothesis, the absence of signs of life is logical. It is because there is none. Or maybe life is not so uncommon, but intelligent species are exceptional. Life on Earth has existed for about 4 billion years, but what we call intelligent life has been around for only 3 million years. Of course, we define intelligence based on our genus, Homo, because this is what we know. But arguably, human beings have been able to send radio waves and spacecrafts to space. No other species that we know of ever did that before for almost 4 billion years. So it tells us that even after the appearance of life, it may take billions of years before intelligence appears. In the case of Earth, 4 billion years is long enough in comparison with the universe, which is 14 billion years old. Maybe the appearance of an outward-looking species like ours is something really extraordinary. And life is maybe abundant in the universe, but intelligent life, able to exit its planet of origin, is something truly exceptional. And that would explain why no trace of extraterrestrial intelligence can be found. Yet another hypothesis, because there are many, is the water world hypothesis. It presumes that planets where life appears have a much smaller land mass than the Earth, or no land mass at all. For forms of life that will develop in water, it is not possible to use fire or develop hands. And even though intelligence is possible, this would limit their capacity to communicate and even more, send objects to space. Other explanations are gloomier. One is that it would be in the nature of intelligent life to destroy itself long before it can establish contact through wars, or maybe disasters provoked by technology, or maybe the existence of periodic extinction on all planets due to natural events prevents intelligent life from moving, traveling, or establishing contact. They go extinct before they have time to do so. If we accept that other intelligent civilizations exist, maybe they are just too far apart in space or in time. If only a few such civilizations appear in a particular galaxy, they may just not have had enough time to meet yet. Following the same logic, the beginning of radio emissions by human beings on Earth is very recent. The first one, the first radio wave emission, was in late 1895. And even though radio waves propagate fast, they have only traveled a very small fraction of the Milky Way yet, reaching only a few hundred star systems at this point, when there are hundreds of billions. For example, extraterrestrials may transmit signals that have a very high or very low data rate, and they may employ frequencies we consider unconventional, which would make their transmission indistinguishable from background noise. Maybe another form of evolution for intelligent life, if it doesn't destroy itself, is that more advanced beings may strip themselves of physical form and transfer themselves to virtual environments that become their universe. They are no longer interested in exploring the physical universe we live in, and space exploration becomes meaningless to them. Or finally, it is possible that the perception that life is meant to expand and colonize is just a cultural feature of our species, born from our minds and the experience of life. Other civilizations may just have no interest in this and prefer to stay in their native world without even thinking about leaving it or exploring the rest of the universe. These are just some of the speculations that have been brought forward to explain the Fermi Paradox. There are more. After all, some people also believe and suspect that aliens are already here. But let's take another look at Andromeda, especially its center. Like for the Milky Way, it has a bulge, a concentration of stars that look more luminous. Since the 1990s, the Hubble telescope has sent better and better images of this galactic nucleus. It contains millions of stars and a massive black hole at the very center. It is believed that galaxies, at least spiral and elliptical galaxies, have such a supermassive black hole at their center. And this is the densest part of every galaxy. Black holes are extraordinarily dense objects that pull other objects due to their gravitational force. We will explore black holes more in depth in a future story. One day, in more than 4 billion years, when Andromeda collides with our galaxy, the two nuclei may merge, or one will be torn apart. We don't know exactly how things will unfold. But we are now approaching the end of our galactic journey. And I hope you have learned a few things about galaxies, astronomy, and physics in general through our adventure. It is time to return to Earth. Now you can let go and sleep. Or if you're not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.